me a lot. Today we are, as you can see, we have already solved 34 problems, and we are starting on problem 34. We will solve maybe 1 or 2 problems depending upon how much time we have, and yeah, let's just get started. So let's look at problem 34, and let us also open a new Jupyter notebook. Let's do the usual thing. Let's call this problem 34, let's call this file problem 34, and let's copy the problem. So this is problem 34, and it talks about digit factorials. So there will be factorials involved and there will be digits involved in these problems. Okay, so that's the problem. So let's read the problem. 145 is a curious number, okay, as 1 factorial plus 4 factorial plus 5 factorial is 1 plus 24 plus 120 is 145. Okay, find the sum of all numbers which are equal to the sum of the factorials of the digits. All right, so that's how do we solve this? So basically we first have to know that for each, we need the factorials for each digit. So let's just create a simple function. It might be even better to create a lookup table for each function. So NP. Okay, and how do we calculate the factorial? So if you have a factorial of 1, so if you want the factorial of 5, for example, then what you do is do np dot range, something that goes from 1 all the way to 6, and you take the product of that. I don't know if you can just do a looks like you can do a product of that like that, and the factorial of 0 happens to be 1. So let's create a lookup table. So factorials, I think we don't need this anymore, so we can get a little bit more space. Factorials equals, we'll create a dictionary for I in range 1 to 10. Okay, and we will say np dot range, everything from 1 all the way to I, like that, dot product. I am slightly concerned of when I equals 1, but let's see what we get. Factorials. So I should do I and that, so that's the factorials. Yeah. From print, and if I do a print of that, then okay, so the factorial for 4 is 24. So we it should be I plus 1. So the factorial for 4 is 24. The factorial of 5 is 120. So it goes all the way to the factorial of 9. That is 362,880. That's the factorial for 9. The factorial for 1 is 1. We also want to make sure that we have the factorial factorials for 0, that is going to be equal to 1. So we have everything all the way from 0 all the way to 9. All right, so next, so if we get any number, we will be able to find the okay, so the next goal is, given a number, we want to find the sum of its factorials. So given a number n, factorial sum, you get a number, and ideally you want to get the factorials, but I will be lazy over here and I will use this is not good programming practice, but I will use global variables factorials to compute the values. So the assumption over here is going to be that the number will have at least one value, so it's not the number is valid in a sense. So how do we calculate this? So for n in number, so for that's I in number, strn, right? So this I is going to be a string, the ith digit of the string and then we'll convert it into an integer, right? And then we need to calculate the factorial of this. So we can just say factorials like that. We know that it should have all the numbers within there, and then we need a sum of the entire thing. So that's what it does. For each number, it takes the factorial and then it takes the sum, and we will just return this. Okay, so that's the factorial sum. So let's check. Sum of 145 should be equal to 145, which is what we get, and the factorial sum of 14 should be 25, which is also what we get. So we have a function that will give us the value. So what do we have to do? Find the sum of all numbers which are equal to the sum of factorials. Okay, so we need to find these numbers. The main question is how many of these numbers we should, so what is the upper bound? So we just need to do something like that. For I in range 1 to we should start with 1 and 2 should not be there, so we should start with 3 to, let's say, 200. And if sum I equals I, then print I. So that's the, and all the way up to 200 there's only one. What about 2000? Okay, so we need to figure out what would be the upper bound over here, because we cannot go on till infinity. Yeah, so we cannot go on till infinity, so we need to figure out what is the point at which we sort of need to stop, the upper bound, so to speak. So how do we deal with this? So let's check a few things. So if we have a number 99, then that will be 9 factorial plus factorial 9 ticked object. So that would, I need a 9 and then a factorial 9 factorial. Okay, so a 2-digit number at most can have 1 2 3 4 5 6 2 3 4 5 6 digits. Okay, that's a two-digit number. So I need at least a 6-digit number. What is this? 1 2 3 4. Okay, we need to go higher. Okay, let's do one thing. Let's say we have, so 2-digit numbers into this. I'll convert this into a string and I will find the length of this. Okay, so for I in range, so let's say we go from a 2-digit number to a 20-digit number. Okay, what we want to do is to see that for an I-digit number, what is the maximum number of digits that will be generated by the sum of the factorials of the individual numbers. So the maximum value for each an n-digit number is n times the factorial of 9, because 9 is the highest digit, obviously. So I will put an I over here, and we see that 19. Let's do 15. So okay, so what does this say? For a 2-digit number, the highest value, the highest value that can be created by the sum of the factorial of its elements is a 6-digit number. For a 3-digit number, it's 7. We want to see where these two are equal. So a 7-digit number, the sum of its digits is equal to 7. That's I need to go all the way up to 7 digits. An 8-digit number will also have a 7. A 9-digit number will also have a 7, and this increases much slower than the number of digits. So I think we can stop over here. Okay, so the highest number that can be created, what this basically means. So let's put 10 here. So basically we have to go up to a 7-digit number, and the 7-digit number, the maximum 7-digit number that we need to go up to happens to be 7 into factorials 9. That's if we have a 7-digit number with 9s, then that's the number it is going to be, which is obviously not the case. So we'll have to go less than this, but let's take this as an upper bound, and let's put this over here. So we go all the way up to this, and we see that we have this number over here, 145, and this number over here, which is 40585. Okay, is that right? It should be. Then okay, find the sum of all numbers which are equal to the sum of the factorials of Okay, so it's basically the sum of these two numbers. Sum of 145 and this whatever this number is. That's the answer. Is it correct? It looks a bit weird. Okay, that's the answer. So this was a really simple problem. Maybe we can do one more. Okay, so we solved problem number 34. Okay, let's chalk this up as solved. Okay, and let's try the next one, 35. Okay, let's open a new Jupyter notebook and let's call this problem 35. Problem 35. This problem maybe, I don't know, I haven't seen this problem, so if this problem takes too long, I will probably stop this in the middle and then we can continue next time. Okay, so okay, let's just copy this. Problem number 35. It's called, well, what do we have? Copy this stuff again. Circular primes. Okay, so we have to deal with primes, and I see a million over there. Okay, the number 197 is called a circular prime because all rotations of the digits 197, 971, 719 are themselves primes. Okay, there are 13 such primes below 100. Okay, how many circular primes are there below a million? All right, so first things first, we have to find the primes below a million, obviously. So let's use our sieve algorithm. We have used the sieve algorithm many times, so it should not be very complicated now. Let's hopefully it's muscle memory by this time. Let's try it. Okay, so nums is let's start with import numpy as np. Okay, and np well, nums, we have a list of numbers that starts from 2 because 1 will divide by everything, so we don't care about 1, and it goes all the way to, so that should be a million. That's 100,000, that's a million. Okay, there you go. It goes all the way to this because this is not a million is not a prime number. We go all the way up to 999,999. That's, yeah, this is also not a prime, so we can yeah, not worry about this. Anyway, so how do we create primes? So we say primes is that, an empty array, and we will keep on updating that while length of nums is greater than 0. So that's our exit condition. We will say primes dot append nums 0. Okay, so we take the first element and put it in the primes, and for the rest of the elements we create a mask equals, these are the things that we want to keep. Anything that is nums percentage nums 0, right? So if this is not equal to 0, so these are all not factors of the first element, then you want to keep them, right? So nums equals not mums the word, but nums, what we are interested in, mask, and we just wait until it finishes. It'll probably take like 7 seconds, 7-8 seconds. If it doesn't stop by then, we'll have to intervene. Ah, it finished. Okay, so 2, 3, 5, 7, blah 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 blah. Do we have a 97? We have a 97, so that's good. Okay. So we have a list of primes. Now, the next thing that we want to do is we want to check if a number is circular. So, oh wait. Okay, so 25 primes are the ones that are less than 100, so we will check with these. Okay, don't worry about length. Okay, so now we need a function that checks whether a number is circular. So define check circular. We take a number and it will return a true or false. So it will take an integer and it will return a bool value. Okay, so what we're going to do is if n is okay, we will just convert it into n. If the length of n is 1, just return true. Okay, that's just a circular number. We don't have to check it. For all other numbers, we have to rotate things. So how do we rotate things? We are going to take this value. We are going to take everything 1 onwards, so this will be BCD, and add something like that. So we are going to rotate. We take BCD and put a at the end, and we have to do it n times. So if n equals length of n, okay, so so it should not return a bool. It should return a list of, what the hell did I do? int values, okay, and this returns a just n, okay, that's what it returns. So we start with a circulars is equals that, and for we just do this n times in n, okay. We are going to take and we are going to add the current value in there, so that's int n, right? And then we are going to do this stuff, except, and we'll say n equals n 1 onward and n 0. This will allow us to rotate this n times, and we will just say like that, type object is not subscriptable. And let's just go with this list. Okay, so let's say we try to check for this, check circular, and we put in the value 1, 5, 4. It well, wait, it should give int 4. Yeah, int 4. I'm surprised that it passed this type check. It should have failed anyway. If you give 45, 45, you should get 45 and 54, and specifically the one that we're looking at is 197. 197. It should give 197, 971, and 719. Okay, so we have a list of primes associated with this. So now what we want to do is to check all the values that are actually primes that are also circular. So we need to do a check all primes, and I give an n, and circular equals check circular. I will get a list of values like that, and for v in that, I want to check whether v is in primes, right? And we have to make sure that all of them are true, and this is it. This is return that. That's all you need. So this is a function like that. So check whether something is a circular prime. So let's say we put in the value 45. It's not a prime, so you will get a false. Let's put in a prime number with like I don't know, primes below 0. Let's say 13. 13 is not a, is it a circular prime? It is a circular prime. 13 and 31 are both 13, wait, 13 and 31 are both there. 73 is still there. 61, yeah, 61 is false. Okay, so the values, okay, for p in primes below 100, if we check for this and it passes, we say, okay, give me those values, and these are the numbers. Let's check. 2, 3, 5, 7, 11, 13, 17, 31, 37, 71, 73, 79, and 97. Okay, so we have got these values, and excuse me, circular primes is that, and what we want to do is find the length of circular primes. So we want to make sure that there are 13 such primes below 100. We want to find the total for this, which is a lot of primes, a lot of values. It's going to take a bit of time. We will give it time. It should not take a long time to finish. What's it called? Still not done? Wow. TQDM dot okay, I need to maybe stop this and see how long it takes. How fast is it converging? So how okay. The reason I am not not doing the addition is because there will be some repeats, and we don't want to do that. So that's the reason why I'm not doing this. Okay, so let me see how fast it's converging. Okay, so it's fairly slow. It's probably going to take a little bit of time. So what I'm going to do is I am going to stop this and check. Okay, so I'll get all the primes over here. Okay, and if this is the case, then I will do plus equals CP plus equals all the primes, and if P in CP so for example 197 I will be checking 3 times, and I shouldn't be doing that. So if it's already if 197 is already there, I will just skip over 971 and 719, because that's the idea. Okay, let's see if that works faster. Okay, this is definitely faster. I can also multi-process. This is definitely faster, but yeah, let's just wait for this to finish. Am I missing something? Oh wait, I'm still finding the primes for this. I can make it even faster by putting this up on top like that, right? Because I should not be checking for primes. So 2% is done in a minute. Let's wait for a minute. %3 is done in a minute. So how do we make it faster? It should not take such a long time to finish. So it's going to take 30 minutes to finish. It's not a reasonable solution. This is not a reasonable solution. Let me see. Let me multi-process this. I will update this. so that this returns a okay. So what this is going to do is it's going to get a list of values, a list of prime numbers, and you give it a number and it will give you a list of the circular primes if it is a circular prime. Otherwise it is going to give you an empty array, so you know not to worry about the rest of the primes. So let me just stop this, okay, and let's make sure that this gives the right thing that we're looking for. So if we get for example 2, we have a problem. Like that. We do get, because all single elements are circular primes, but if we provide, for example, 13, it's going to give us I should append it like that. It should give us 13 and 31, those are circular primes. And if I get 61, for example, although 61 happens to be a prime number, sixty-one happens to be a prime number. So this one should allow us to get a list of primes faster, because we are not looking for all circular primes, or looking to check for all numbers whether they are primes. And this additionally has the advantage that we are going to be able to multi-process this. Okay, so let's bring all of this down over here and let's multi-process this. So we start with CP, and for V in P dot I map unordered, like that. I want to map get circular for all primes, okay, and I will put TQDML over here. This is going to return the list like that, and I will just add it to list of circular primes, and I will just add it in over there. So yeah, I also should check whether something is within P. If it is within P, I shouldn't check it. So I'm using a global variable, so if it's already in, then we okay. So let's just do this first. See whether this speeds up computation. TQDM total is equals length of primes. Let's see whether this is much faster. Okay, this is probably something that will finish within a reasonable amount of time. But this is going to have a lot of duplicates, so we have to take duplicates out of this. I'm sure there is a better solution to this. I am sure there is a better solution to this. Let's finish this. Let's wait for this to finish, and then after that we're going to see how we can improve the quality. I've been online for about an hour or so, so this has been a long video. Yeah, this is too slow. So about 2 minutes to finish about half, so it'll probably take 4 minutes to finish the whole a little less than 4 minutes to finish the whole thing. I'm guessing we don't need to go all the way up to here because of symmetry. I'm guessing that we only need to go halfway. For each n-digit number, I only need to go halfway, something like that. Okay, so now is 212 values, but I'm guessing that it is going to have a lot of repeats. So what I'll do is I will say this is equal to list set like that. How about now? Much fewer values. Okay. Only 55. I don't know if this is correct. I don't know if this is correct. It is correct. Wow. All right. So we'll stop over here. If you like this, then please subscribe, and I will see you next time. Bye bye.